Okay, so let's look at the remaining 4 review problems. These problems are from chapter 23, and the first one involves the wall of an aquarium. It says an aquarium filled with water has flat glass sides whose index of refraction is 1.56. A beam of red light with a wavelength of 680 nanometers in air strikes the glass at a 43.5 degree angle. So let's look at this. We have a situation here where we have air over here, which is N equal 1. Then we have our glass. That's N equal 1.56. And then over here we have water. Of course, that's N equal 1.33. So we have all of our indices of refraction. We have a beam of red light that strikes at an angle of 43.5 with the normal. So our normal would be like this. We measure angles from the normal. That's 43.5. All right, first question. What is the angle of the light reflected off the air glass interface? Well, that is the easiest question because the law of reflection says the angle of incidence is equal to the angle of reflection. So part of this beam is going to be reflected. So it will reflect at 43.5 degrees from the normal. Part B says, what is the angle of the light when it enters, and that's supposed to say into the glass. So for B, we use Snell's law. NA sine theta A is NB sine theta B. So we're incident in air at an angle of 43.5 degrees into glass, 1.56 at an unknown angle. The one thing I do know is since it's going into a more optically dense medium, it will refract towards the normal. So I expect this angle to be less than 43.5. If I divide both sides by 1.56, I just need to do a sine inverse. So sine inverse of 1 sine 43.5 divided by 1.56. Be sure if you're doing this all in one step that you're being careful with your parentheses and everything. And I get the answer is 26.2 degrees. Okay. Part C says, what is the angle of the ray when it enters the water? So now it's going to go from the glass into the water. So now if we use Snell's law, we have the 1.56 sine 26 point, I'm going to not round so much, 1.84 equals, I'll call this 1.33 because we know the index of refraction there for water. Sine, I'm just going to call it theta C just because it's the third angle. One of the things I want you to notice here is this is exactly the same as this, which was exactly had to equal this. We could have used 1 sine 43.5 has to equal 133 point sine theta critical because these two are exactly the same. All right, so we solved that. Again, we just have to use an inverse sine, so I have 1.56 sine, I'm going to use my previous answer in my calculator, divided by 1.33, and then I take the sine inverse of that, and I get 31.2. I'm not surprised that it's bigger because it moved from an index of refraction of 1.56 into water, which is 1.33. When it moves into the less dense medium, it refracts away from the normal. Okay, let's carry on. Question D says, what is the wavelength of the light in the water? Well, the wavelength of the light in the air was 680. So if I want the wavelength in the water, then I'm going to say lambda equals lambda 0 over n. This is the wavelength in a vacuum or in air. And then divided by the index of refraction. So for water, it's 1.33. 680 nanometers divided by 1.33. And I get 511 nanometers if we're keeping 3 significant digits. If we're only keeping 2, which is probably more realistic than 510. All right, E says, what is the wavelength of the light in the glass? Well, that's the same problem, just a different index. 680 nanometers in a vacuum or in air divided by 1.56. And that comes out to be about 436 nanometers. Just want to make sure we remember that wavelength changes, frequency does not. Which brings us to questions F and G. What is the frequency of the red light in water? What is the frequency of the red light in the glass? Well, why don't we find the frequency of the red light in air, and that will give us the answers to both F and G. I know C equals F lambda. If we are in air, actually we usually say V, but since we're in a vacuum or air, this is 3.00 times 10 to the 8th equals the frequency. It was 680 nanometers, so 10 to the negative 9. If I solve for F, that's going to give me the frequency for water, air, glass, any medium. 3 times 10 to the 8th divided by 680 times 10 to the 9th. Or I'm sorry, 10 to the negative 9 nanometers. And we get 4.41 times 10 to the 14th hertz. Remember, visible light, the frequency is always on the order of 10 to the 14th. So pretty straightforward questions. Just want to make sure that you understand Snell's law, law of reflection. Frequency remains the same when we change mediums, but wavelength doesn't. All right, problem 5 says, now consider the same aquarium from problem 4. At what angle would a light beam inside the water need to strike the glass wall, so that the light inside the glass wall is totally internally reflected? So here's the picture. And they're saying, let's consider this red beam of light. What angle does it have to hit the glass? Remember, when it goes from water, it's in the water. So this side is water over here. Here's air. Here's glass. What angle does it have to hit so that when it refracts, and it is going to refract towards the normal, it's going to be totally internally reflected and not actually escape into the air? This is 1 for the index. This is 1.56. This is 1.33. Remember, you only get total internal reflection when something is trying to go from something more dense into something less dense. We don't get it from light inside the water hitting the glass, but we can get it from glass into air. All right, what angle would the light beam need to strike inside the water need to strike the glass? We want to know this. What angle here is going to cause total internal reflection? First, we better find the critical angle for the glass-water interface. All right, remember, the critical angle means that the refracted angle is going to turn out to be 90. So we would have 1.56 sine theta critical equals 1.00 sine 90. Well, all of this right-hand side is just 1. So our critical angle is simply 1 over 1.56. Remember, it's NB over NA. When you're trying to go from something more dense, you start off in something more dense into something less dense. So, critical angle, I just did that sine inverse of 1 divided by 1.56. And I find out that the critical angle is 39.9 degrees. If this angle inside here is greater than or equal to 39.9, I'm going to get total internal reflection. I just have to figure out what this angle in the water is, my incident angle, theta A, and let this be my theta B. And I can figure out what theta A is. So, Snell's law, NA sine theta A, NB sine theta B. So 1.33 sine theta A would have to equal 1.56 sine 39.9. Same thing I've been doing. I'm going to solve for theta A. 1.56 sine 39.9. Close those parentheses, divided by 1.33. Take the sine inverse. And I get theta A is 48.8. So the angle in water has to be greater than or equal to 48.8 degrees. And the result of that is going to be that the angle in the glass is going to be greater than or equal to 39.9. And you will get total internal reflection. All right, last problem, we're going to look at polarization. It says two polarizing filters are oriented at 36 degrees to each other. A beam of light polarized at an 18-degree angle to both filters and with an intensity of 100 milliwatts per centimeter square passes through both filters. What is the intensity of the transmitted light? So let's think about it. There's two filters. Let's draw them. There's one filter. If we let its polarizing, let's say it's vertically polarized, and we call that 0 degrees, then the other filter is polarized at 36 degrees because they're polarized at 36 degrees to each other. A beam of light polarized at an 18-degree angle to both filters and with an intensity of 100 milliwatts per centimeter square passes through both filters. Okay, the only way that the incoming light, I'm going to draw the incoming light blue, can be polarized at 18 degrees to each of them is if its electric field is vibrating back and forth, it's linearly polarized at 18 degrees. In other words, it's 18 degrees from this 0 degree filter, and it's 18 degrees from this 36. It's right in the middle, but it's linearly polarized. So what will be the intensity that comes out? All right, our formula says I equals the initial intensity times cosine squared phi. So if we look at the first filter, that is going to be 100 cosine squared 18 degrees, because the angle between 18 and 0 is 18. This is going to be our input for the second filter. So this is like the new input, 100 cosine squared 18 degrees, cosine squared. Okay, from here to here, light passing through this 0 degree filter will come out at 0 degrees to this 36. This is an angle of 36 degrees. And that's going to be our answer. If we wanted to, we could have done it step by step. If I did 100 cosine 18 times cosine 18, the original 100 milliwatts per centimeter squared, we get out about 90.45 milliwatts per centimeter squared. But that's going to go in right here, and we're going to multiply that times cosine 36, and I get 65 point, oops, sorry, I did not do that right. Let me retype that in. 100 cosine 18, and that gives us a 90.45 times cosine 36, and I get 59.2. I'm glad I remembered the correct answer. I just have typed it in on my calculator. So 59.2 milliwatts per centimeter squared. The problem I actually took this from actually just asked what percent passed through, but rather than ask what percent, I just told you the initial amount was 100. But if you wanted to know what percent, then clearly this was 59.2% of the light made it through both filters. Okay, that is the solutions to the practice problems. If you have questions about them, you can certainly email me, and I'll see you bright and early for the test.